I'm shooting at the rate of 60 frames per second using a Canon T7i. We cannot see the blinking, unlike the iPhone 4S. We can see the blinking of this LED. Here we cannot see it. Here's all smooth. And then this new project. Problem solving for the rectifier. Let us see. We're going to solve for the voltage BP, voltage peak at the secondary, voltage average without capacitor at the load, current average without capacitor of the load, ripple voltage, delta B, R1 value of the load resistor, BP, voltage peak of the load, efficiency, theta, Greek symbol, eta, for of the rectifier, voltage RMS of the secondary, output frequency, and then the peak inverse voltage of the rectifier. Okay, let us now proceed to the computations for this problem solving. Let's go back to our discussion. In the figure 2, we have the full wave bridge rectifier without capacitor. So this is now the schematic diagram for solving the problem. We disconnected the capacitor. What remains here, what's left is the load, the rectifier, transformer, and then the alternating current supply. Okay, quick review. A big sine wave at the primary becomes smaller sine wave at the secondary. What is the voltage here? 12 volts. BRMS. Still, the 12 volts is BRMS, or alternating current, or 12 volts AC at the secondary. And the sine wave is, the wave is like this, smaller sine wave. To the rectifier, the rectified output is the two pulsating or the two half cycle. These two output waveform of the rectifier, which is also the same waveform output of the load, because now the output waveform or the output of the rectifier will now going to supply to the load, and this is the output waveform of the load, the same as the rectified output of the rectifier. Oh, we just disconnect the capacitor. What we're going to solve, what is necessary here? Voltage average. What is this voltage average? That is the effective voltage. What is the voltage across the load? That is our priority, or that is the most important problem we're going to solve. Voltage average, the equivalent DC at the load, DC current at the load, or the recurrent at the load, voltage average. Let us now proceed to the computation. going to compute for the BRMS of the secondary. What is the BRMS of the secondary? BRMS of the secondary. As I've said, when you are buying a transformer, it has a voltage rating of 0, 12 volts. We're going to use 12 volts. So if you're going to use 12 volts, that is now the voltage BRMS. 12 volts BRMS given in the transformer when you are going to buy the transformer. So the voltage BRMS of the load given at the transformer, that is 12 volts. When you buy a transformer, voltage rating of 12 volts output. The secondary where you're going to use, it's the BRMS. So 12 volts is the BRMS of the secondary. Okay, we now come to the voltage peak at the secondary. Why do we need to solve for the voltage peak? Because we are using voltage peak for computation. Where is that voltage peak? If this is the sine wave of the secondary voltage or the 12 volts sine wave, voltage peak is located at the topmost or the peak or the crest. That is the voltage peak, or they call it Bmax, voltage maximum, the same as voltage peak, BP. Voltage peak at the secondary, we know that, located at the top of the sine wave. That's why they call it voltage peak. I denoted S here because we are using BPS referring to secondary, BPS. So let us make this BPS for computation our voltage peak secondary, just to simplify the problem. And then we got now a formula for the voltage peak. Voltage peak is equal to BRMS divided by 0.707. That is the formula. This is already a formula. So voltage peak at the secondary, we know the voltage RMS, which is given from the transformer 12 volts and then 0.707. Simplifying, BPS now is 16.973 volts. So if this is the sine wave of the secondary, this one the same, voltage peak at the secondary is 0.166.973 volts or 16.973 volts. That is now the voltage peak at the secondary. So we solved the second problem, voltage peak at the secondary. And then here, what else is the problem here? Now we're going to solve this voltage peak at load. What is the voltage peak of the load? If this is the waveform, what is the voltage peak of the waveform of the load? Here at the topmost of the wave, voltage peak of this load, which is the same as the voltage peak of the rectifier, because this is the one supplying the voltage. The rectifier is supplying voltage to the load. That's why they have the same waveform. Okay, you can compute the voltage peak of the load using the formula BRMS is equal to BPL over square root of 2. Again, I'm using BPL to denote that this is a voltage peak of the load, because the regular voltage peak is BP. So when BPL, the L here refers to the load. BPS, S here refers to the secondary. So BPL is equal to, using our math knowledge, crisscrossing BRMS divided by 1. BPL now, crisscrossing mathematics or math knowledge, becomes BPL, and then the square root of 2 multiplied to the BRMS. We know the BPE BRMS, 12 volts already. Square root of 2 now multiply, and then we got voltage peak of the load 16.92 volts. Where is that? Voltage peak of the load is this, the orange one, which is the same as the voltage peak of the rectifier, because the supply is the supplier, or the one supplying the voltage here is the rectifier. That's why they got the same waveform. Almost the same as the voltage peak of the secondary, BPS 16.973 volts. Here 16.92. Why? Because the peak remains, or the waveform is the same. The voltage peak of the load, of the rectifier, and of the secondary is the same. Almost the same. 16.92 for the load, and for the secondary 16.973. Voltage peak of the load the same as voltage peak of the rectifier. That is now the third solution. Voltage peak of the load. We now come to the next problem here. Let us see what is this. We have here voltage average of the load. This we are what we're waiting for, the voltage average. What is this voltage average? Voltage average, that is the effective voltage, or the voltage, the recurrent voltage. That's the voltage across the load. That is the voltage average. We are averaging the waveform, because still this is pulsating DC. That's why the pulsating DC has a voltage average. That is the voltage average. The voltage average is equivalent to the voltage DC, or the effective voltage, because still the load supplying the voltage supplied to the load is still pulsating DC. That's why they call it effective voltage average. Let us compute the voltage average, or the voltage across the load. That is the voltage average. Averaging the voltage, because still it is pulsating DC. There is a formula for that. Voltage average equal to 2 times the voltage peak of the load divided by pi. That is already a formula. What is the location of the voltage average? It's located near the peak, somewhere here. Voltage average. Remember, voltage peak is here, and voltage average somewhere here. BPL, we already computed that, 16.92 volts by its substitution. Pi is equal to 3.1416. That is mathematics. Voltage average is 10.77 volts, located somewhere almost near to the top. 10.77 volts. There is another formula for that. Voltage average is equal to 0.636 voltage peak. Another formula, 0.636 BP, big voltage peak, and the result is the same, 10.77 volts. That is the voltage average of the load, located near the peak of the voltage. Okay, voltage average is equal to the equivalent DC voltage, that is the voltage pulsating DC, to the load effect, which is the effective voltage. They call it effective voltage. That's why we need to compute for the voltage average, the voltage supplied to the load, which is a voltage DC, or the pulsating DC voltage across the load. That is voltage average. Okay? And then the next problem solving is the load resistor. Why do we need a load resistor? To limit the current flows at the LED. Because if this is the LED, the symbol, this one, it has a forward voltage of 12 volts. To turn on this type of LED diode, light emitting diode, we need at least 2 volts to turn on or to light this LED. We are now designing a load which is composed of LED and a series resistor. That is our problem. This is the symbol, the same diode, forward bias from anode to cathode, positive, negative, when the current should be flow at this direction. We need the 2 volts for this diode to turn on. What is this 2 volt? Where did I get that? From the datasheet of the LED. Usually in standard computation, I use 2 volts for all types of LED. There are so many types of LED with different voltage rating. But for computation, standard computation for the LED, I use 2.0 volts voltage of the LED to turn on. Because we're designing an LED, which is our load, to light the LED. That is the voltage rating of the LED. And then there is a forward current. What is the current to turn on this LED in order not to burn? This is 0.02 ampere, or equivalent to 20 milliampere. 0.02 ampere is slide 2 zeros, 3, it becomes 20 milliampere according to the mathematics. 0.02 ampere, just slide it to the right, times 3 milli times 3 to times 10 to the negative 6. This is mathematics. 1, 2, 3 becomes 20 milliampere. That is the current rating of the LED according to the datasheet. This 0.02 ampere is my standard value for computing the current flows into the LED. That is the necessary current to turn on the LED. And because we don't know the current flows here, but we know the current 0.02 of the LED. We're designing a load composed of LED with a current of 0.02. So it means the current flows here is 0.02. Let us now check the solution to the problem. We're going to compute for the value of R1 to limit the current flows at the LED. Here, what do you think is the voltage supply? Where is the voltage supply here? The voltage supply here is from the voltage peak of the rectifier, which is equal to voltage peak of the load. Remember, this is already rectified, so there is a voltage supply here. So that is now the voltage supply, the voltage peak of the rectifier, which is equal to the voltage peak of the load, the same waveform. BRR, voltage peak of the rectifier, is equal to the voltage peak of the load. Same peak. We're using voltage peak in the computation of the waveform. Remember that. So if this is the voltage supply, the voltage peak of the rectifier, which is equal to the voltage peak of the load, the same waveform. This is now the supply, this is now the load. We're taking the KVL. Kirchhoff's voltage law. Kirchhoff's voltage law states that the sum of all voltages in a closed loop is equal to 0. Kirchhoff's voltage law, KVL, at voltage peak of the load, which is equal to the voltage peak of the BPR, voltage peak of the load minus to the voltage peak of the load to the resistor to the diode. That is the whole KVL. So for the formal KVL computation, we got supply and then the load. Voltage peak of the load, the supply voltage minus the voltage of the load. So BPL minus BR1, voltage drop at the D1 is equal to 0. This is now the KVL. BPL, BR1, BD1 is equal to 0 according to KVL. Transposition becomes BR1, BDL minus BD1. Substitution, we know the voltage peak of the load, which is 16.92 volts. And then the voltage rating of the LED, see, 2 volts. We already know that. That is the required voltage of the LED to turn on. And we got a voltage drop of 14.92 volts at the R1 or our load resistor. Okay, using Ohm's law, B is equal to IR in terms of R1. R1 now is equal to B over I. R1 by substitution, we know that 14.92. And then the current rating of our LED is 0.02 ampere. Why did I use 0.02 ampere for the current of this R1? Because the current in series is equal. Whatever the current of the LED in the LED is equal to the current of the R1 because they are in series. Current in series is equal. Current law. Kirchhoff's current law. Why did I use 0.02 ampere? Because we're designing a load made of LED and a resistor. That's why we got a voltage drop here at the LED, which is 2 volts, and then the current rating of LED 0.02 ampere or 20 milliampere. Simplifying, 14 divided by 0.02, we got 746 ohms. I don't have 746 ohms. I use 1 kilo ohms, my available resistor. And it is okay. So the value of the load resistor now, to limit the current flows at LED in order not to burn out the LED, in order not to damage this LED is 1 kilo ohms. So we solved now already the load resistor, 1 kilo ohms. Let us now come to the next problem, and that is I average or average current at load. Okay, this is the analogy. If there is a voltage average, there is also a current average. So in the formula of Ohm's law, VIR, so voltage average is equal to current average. That is the analogy. Transposition, we know the voltage average. We solved that already here. 10.77. And then the resistor, 1000 ohms or 1 kilo ohms. We got a current average of 0.01077 ampere. So if this is the voltage peak, there is also in the graph current peak. If this is the voltage average, there is in the graph current average. That is the analogy. Current average. And we're going to use that in the computation of ripple voltage. Okay, we solved already the value of current average. Average. Now, what's the next? Is this. The efficiency Greek symbol eta of the rectifier. How efficient the rectifier is. Is it okay? Nice? Good? We have a formula for that. Eta, Greek symbol for the efficiency, eta, we use that, is equal to the power of the load or the power output divided by the power input times 100%. That is the formula for the efficiency of the rectifier. Power output divided by power input times 100%. We have a power formula. Power formula P is equal to BI. We know that. And Ohm's law, VIR or current is equal to V over R. Substituting the value of I to the power formula, we got now this. P is equal to B times, before it's I, now it becomes V over R because of the Ohm's law. Simplify, P is equal to B squared over R. That is now the power. So, power output or the load is equal to B squared over R. Or equal to voltage average squared over R. Or equal to voltage DC over R. That is the voltage average or equivalent DC current that flows into the load. They are all the same. And to the input, we're going to use the BRMS of the secondary. Remember that BRMS is the input. This, the BRMS here, is the input power over the output power of the load to the input. That is the efficiency. Okay? Same, B squared over R or BRMS squared over R. Remember, BRMS, secondary, still alternating current. Here, it's pulsating DC or the voltage average. Substitute it to the equation. We got now this. BD squared, see, BD squared, power output, over R. BRMS squared over R. Cancel out the R. What remaining here is the 100% and then the BDC squared and BRMS squared. Substitution, we know the voltage average. Remember, voltage average 10.77 and then the RMS 12 volts given in the transformer. Voltage average, we computed that. Simplifying, divide, and then times 100%, we got 80.55% efficiency. That is the efficiency of a full bridge rectifier. And we computed now the efficiency. of the rectifier, which is very nice. We now come to the next problem solving, and that is this PIV. What is this PIV? Peak inverse voltage. The requirement for the PIV of the rectifier, the diode, the 1N4001-007. Peak inverse voltage should be greater or equal to voltage peak of the load. Should match to the voltage peak of the load. Should be greater than or equal to the voltage peak of the load. We're always using the voltage peak for the computation. What is this PIV? Okay, let's go back to the circuit. Remember, during the positive half cycle, diode is forward bias. How about negative cycle? During the negative, it becomes reverse bias. See? Forward and reverse bias. If we're going to use this, the diode, during the negative half cycle, if it connects to the voltage supply and the current that flows is alternate, during the reversal of the wave, reverse direction, remember the reverse direction, it becomes reverse bias. This is forward bias for the first half cycle, and for the second half cycle it becomes reverse bias. And this PIV refers to the how long will it take, how durable, how will it take to withstand the reverse bias condition of the diode during the reversal of the wave. See here? How long will it take? We need a peak inverse voltage to counter that first reversal of the wave, or the reverse direction of the wave, or the reverse bias condition of the diode. We need to counter that. We need a peak inverse voltage value for the diode, or else it will burn out during the reverse direction of the wave, the reverse bias condition of the diode. Forward, and how about the reverse condition for breaking this junction barrier? We need to counter that, so that's why there is a peak inverse voltage. What is the value of that voltage? Should be greater than equal to the voltage peak of the load. Voltage peak of the load 16.92 volts. Therefore, peak inverse voltage is 16.92 volts, greater or equal to. That is the requirements of the peak inverse voltage. For 1N4007, there is, in the data sheet I read, it's 1000 volts peak reverse voltage, or when you're matching with RMS, it should be 50 volts BRMS for the BRMS, but we are only using 12 volts BRMS, and then 12 volts voltage peak, see, or the voltage peak 16.92, but the voltage repetitive or voltage PIV of this 4007 is almost 1000 volts, but the voltage peak of the load is just 16.92 volts, so it's okay. RMS of the transformer 12 volts, but for the diode, according data sheet, 50 volts RMS. the capacity. That is now the peak inverse voltage, the reverse voltage of the diode necessary in order not to burn out. Let us now compute for the output frequency. The output frequency is denoted by FO. FO, frequency of the rectifier output or the load. Frequency of the load, that is the we're going to compute. In this graph, this is a sine wave from the secondary windings. Input frequency, Fi, of the secondary windings of this. Input frequency of the secondary windings, and we're going to compute for the output frequency of the load. This is equivalent to 1 period, Ti, input time period, Ti. 1 period, that is the cycle. For the rectifier or for the load, the same output frequency, Fo. So To refers to the time period of the full wave rectifier or the time period of the load, the same waveform. Remember, the same waveform, the same output. Rectifier and the load. As you have seen here, for the full cycle, full wave, time period of the half wave is time period of the output of the rectifier is 1/2 of the 1/2 of the input period from the analysis. Should be connected like this. See? Which is twice for the whole cycle, twice time period of the input. Twice of this. See? So we get one equation 1 here. Since we know we have an equation that frequency is equal to over time period. This is already a formula. Since we know that we have a formula of transposition, time period now, in terms of I, 1 over Fi. So we got equation 2. This is already a formula. So if Ti is equal to 1 over Fi in terms of To, output, To is equal to 1 over Fo. That is the equation 3. So we got 3 equations. Using equation 2, Ti is equal to 1 over Fi. We know the input frequency of the secondary, 60 Hz. Remember? 60 Hz primary, 12 volts, still 60 Hz. One over 60 Hz in terms of time, that is now the unit of period. 1 second is 0.01667. That is now the Ti. We have another formula. Since we're using equation 2, now we're going to use equation 1 from the analysis of the graph. Ti is equal to twice To. Remember, for the whole cycle, To is twice the 1 cycle of the sine wave here. 1/2, only 1/2. Double the output, twice of the time period. Equation 1. Substitute, crisscrossing, when we need to know now the output period. To now is equal to Ti over 2. Ti over 2 from this equation. Substitution Ti, we know that Ti divided by 2, we got the output period of 0.0083 seconds. Now, let us now use equation 3. TO 1 over FO. Therefore, FO 1 over TO. Crisscrossing mathematics. Substitution, we know that TO, it becomes now the frequency output is 120 Hz, twice the input frequency of the secondary. That is the output frequency, 120 Hz. So, in this design, we got an output frequency of 120 Hz to this load, and the input frequency of 60 Hz. 60 becomes 120 Hz to the output. Can you hear that sound? That is a frequency. You can connect it to the amplifier and you can hear this 120 Hz. That's why there is a hum sound in the power supply. If there is something wrong with the rectifier. So we calculated that. Next, we're going to compute for the ripple voltage or the voltage average. What is now the equivalent voltage or the voltage average that flows into the load? That is the voltage average with filter capacitor. It is different now. So we get a schematic diagram again. This time we have the capacitor. We connected the capacitor to filter the waveform from this type of pulsating into this ripple voltage, pulsating DC with smooth and filtered waveform that flows in just one direction. So we know that the voltage peak of the load, at the peak, voltage average is somewhere located near the peak. Now we're going to compute for the voltage average. The equivalent voltage or the effective voltage with capacitor that is necessary to supply, that is this necessary supply for the load, the voltage average. What is that? Or the voltage of this load. See, this is the ripple voltage. Ripple voltage. Okay, what is this ripple voltage? That is the ripple voltage produced by the capacitor. AC component produced by the capacitor. AC component of the wave, that is the ripple voltage. We get a formula for the voltage average. In voltage average, this is already a formula, voltage peak minus delta V, which is the ripple voltage divided by 2. That is the formula 1. Here, we know the voltage average, voltage peak of the load, but we don't know the ripple voltage. Delta V denoting that this is a ripple voltage. Where can we get the ripple voltage formula? We can get that from what is the current in the capacitor. There is a current here. There is a current formula for the capacitor. See this? What is the current in the capacitor? We have a formula for that. I, current of the capacitor, is equal to capacitance, the derivative of voltage divided by derivative of time. Calculus. Due to the variation of the voltage over the variation or time interval. dB over dt, that is calculus. The variation of charging and discharging of the capacitor, that is the effect of charging and discharging of capacitor. In terms of algebra, we can rewrite this differential calculus into algebra. I average is equal to capacitance times the delta B or delta T. dB becomes dB delta B delta T. Algebraic expression of this formula. And delta B period of the discharging and charging of the capacitor is 8.33 milliseconds for the full wave. That is given. It's constant for the full wave. So in this formula of the current to the capacitor, we have this ripple voltage that we are going to substitute to our first equation. So we have now the second equation here. Capacitance times ripple voltage over the time interval, so delta T. Since we know the current average, we computed that. Remember this. .0177. Value of the capacitor 3300 microfarad. Now the delta B or the ripple voltage we don't have, and then delta C, that is constant already, 8.33 milliseconds. By transposition using our math knowledge, delta B now is 0.01007 times 8.33 milliseconds divided by 3300 microfarad. Simplification, millisecond become 0.00833 seconds. Farad now becomes 3300 microfarad becomes 0.0033 farad. And now the ripple voltage is 0.27186 BP. Just simplification. Voltage peak to peak. What is the voltage peak to peak? If this is the sine wave, there's a peak here, another peak at the bottom. When you compute voltage peak to peak from here to here, that is the voltage peak to peak. Since this is ripple voltage, this is the AC equivalent component produced by the capacitor. Ripple voltage here. Remember, ripple voltage, there is AC component. If this is the ripple voltage, there is still an AC component of the wave. Voltage peak to peak. By substituting the value, now voltage average from formula 1, substitute from what we computed, voltage peak, we know that 16.92 minus the ripple voltage peak to peak, divided by 2, simplify, and we got 16.906 volts voltage average when we're using capacitor. So, without capacitor, our voltage average is 10.77 volts. That is the equivalent effective voltage across the load. With capacitor, it improves. It becomes 16.906 volts with the use of filter capacitor to the circuit. So we computed everything, and let us now see. Okay, this is now my design. This is my layout, PCB layout, the transformer, and then the schematic diagram. I had the output header for the provision for the voltage regulator, and then I have a header here for the transformer to connect to the PCB. That's the header here, header. And this is now the final product. This is the transformer, the secondary, and then this is now my full wave rectifier. 4 diodes, 1 LED, 1 resistor, 1 kilo ohms, 2 header. Header of the transformer, capacitor, perf board, some jump wires, I solder it, and we get now this. That is the full bridge rectifier. This is now the final product. Just connect it to the secondary of the transformer. Let us see. Okay, and then let's check. Connect it to 220 volts. 220, 3-prong, and we have now this, a full bridge rectifier. Let us now see the actual secondary. Let us disconnect first 220, and as you have seen here, I disconnected the 220. Now, as I've said, the one who is supplying to the load is the capacitor, the discharging effect of the capacitor. Then it's fully discharged. I disconnect 220 volts. Now we're going to place the transformer and close the speaker box. Okay, disconnect that. It's wrong. This way. Then connect again the 220. I use 3-prong. We have now the output, and it's not pulsating. We have the cover here. Where is that? We have now this, a full wave rectifier. With an output LED. Okay? There's a screw here, I didn't yet screw it. So, thank you for watching the video, and this is now our full wave rectifier. Let us check the other lines of the project. Let us see the other project. Okay, we got now 5 rectifiers. Rectifier here. 1, 2, 3, 4, 5. Since I'm using a different camera, we cannot see the blinking pattern of the LED. I'm shooting at the rate of 60 frames per second. Using Canon E7i. You cannot see the blinking, unlike the iPhone 4S. You can see the blinking of this LED. Here you cannot see. And then this new project. So, thank you. Bye bye.